I know the audio of these YouTubes is not great.
As a galaxy rotates, light from the parts approaching the observer are blue shifted, while light from the parts turning away from the observer are red shifted.
So when you look at a galaxy, now first off, you will not see this with your eyeballs. This is something that can show up that a computer can pick up when it's connected to a proper telescope. But if the galaxy is in fact rotating like this, then the part of the galaxy that's rotating towards you will appear blue shifted, and the part that's rotating away from you will appear red shifted, and this part that's perpendicular to you, hint hint, does not really appear shifted at all.
By measuring these shifts, astronomers determine how galaxies rotate.
And so there you have it. Although, again, you will not see this rainbow when you look up into space. That would be pretty cool, actually. Um, Another way we use this is actually something called this Doppler effect here to figure out actually whether there's a planet orbiting a star, called the radial method. And so, sorry this video is a little choppy, but when we look up now looking for planets around other stars, you can look at a star, and if you are positioned, let's say the Earth is over here, much farther away of course, but over here, if you look at that star and the star appears to do this little side-to-side wobble, well, that's an indication that there is a planet that's gravitationally pulling on it as it orbits. And you can actually pick up this side-to-side wobble. You don't actually see the wobble. What you do see is that at times the star appears to be red-shifted, like now when it's moving away. And other times the star appears to be blue-shifted when it's moving toward. And from that, if you get a nice periodic red shift, blue shift, something like this graph here, you can actually plot it out, and then you say, oh, look at that. It's got a velocity here's negative, away from us, toward us, away from us, toward us. And if this repeats, you actually can say, wait a minute, there must be a planet around that star. And this is one of the methods used to discover what we call extrasolar planets or exoplanets, planets around other stars. All right, we're a little choppy. Let's see if we cut some of these out. It might help us. Okay, so let's go back over here and let's answer these questions about this picture. So here, this telescope is looking up at this star, and so you're getting some sort of Doppler effect. Actually, it's looking up at a galaxy. How is a galaxy moving? Well, if the frequency comes through greater than expected, of course, is higher frequency, which is blue shift, well, then we can essentially take this comment. How must it be moving? So we're going to reverse this. The blue shift would then tell us that the galaxy is approaching us. Now, we could be approaching it, it could be approaching us, or both, but it doesn't particularly matter. What matters is that we are approaching each other one way or another. If it is steadily increasing, well, the simplest version to say is it is, again, moving toward us, and not only that, it is accelerating toward us. Now, yes, some of you may realize you could have a steadily increasing frequency which is actually redshifted and becoming less redshifted, but that is still accelerating toward us even though it's moving away from us. Okay, so as expected, let's go use our green for that one, kind of our mid color. So we have no relative motion. Steadily decreasing is going to be a redshift, and most likely a redshift. And this will be accelerating away from us. And I suppose if you really wanted to be picky, this is likely a redshift. Up here, this steadily increasing was likely a blue shift. It is for certain, though, that it's accelerating toward. Here is accelerating away. Less than expected. That's a red shift. And that is receding from us. Let's put that in red. And finally, question down here, which way is the star in the wobble picture revolving? There are a few reasons you should know this here. First off, look at the wavelengths. In this case, follow your intuition. It looks stretched out. Here you actually see it's red. But it looks stretched out. That's bigger wavelength, that's smaller frequency, that's redshift. This must be moving away. In this case, on this side, the star, the waves look squeezed together. It must be approaching, moving toward. So your rotation is actually this way. Depending on your perspective, you can call that clockwise or counter, but I'll just put a couple of arrows on there. Let's see how drawing goes. Let's try green. So it's going to go this way on the back side, this way on the front side. There we go. Good. So that gives us a general idea of Doppler. I'll show you a couple cool things that we did not talk about previously on page 40. You are now empowered to do all of WA16, so you can finish that. I'll show you the key for pages 1 and 2 in a separate video shortly, but this basically has us covered. Now, the cool thing is, here, let's let this go. Our object was never moving faster than the speed of the waves. But can that happen? And the answer is yes. Now with light, no. But with sound, it can. And so here, let's say if we're moving at 20, but the speed of the wave is 80, the waves will always get away from us. If we increase our speed to 40, the waves still get away from us, but notice it's more bunched. So the Doppler effect is actually greater. We said this back in the notes on page 40. Get our speed up to 60. 61. Notice the Doppler effect here is still greater. So the frequency on the lead side or the approach side is very high. And on the tail side, the recede side is very low, big wavelength. But something interesting happens when we get all the way up to 80, when the source actually matches the speed of the wave itself. So when this makes a new wave, it's going to move away from it at 80, but the source is also going 80, which means it's going to keep up with the waves it makes. And check this out. That means it's going to be making waves on top of the last wave that it made, on top of the last wave that it made. They're going to stack up. And that's actually what you see here along this leading edge. The wave fronts are stacking up. Let's show that again. So when that happens, you actually get this wave of constructive interference. Lots and lots of compressions on top of each other. In fact, you could even go ahead of the speed of the wave, where you can in fact run ahead of it. But still, you'll actually get this line of constructive interference. It's actually a cone in 3D space. Let's go up to 100 as the max this does. And this can be done. You can fly a plane at basically 25% greater than the speed of sound. And if you notice, all of these waves tend to line up in this cone, this sonic cone. Looks like a triangle on here. Now, if you are standing here, let's say you're standing above the letter D in speed, notice the plane, or whatever's making the sound, has passed overhead. but you haven't heard it yet. In fact, you won't hear it until, oh, I missed the pause. Let's try it again. You won't hear it until now. So now the sound wave hits you. Notice the plane is way ahead of you, so you'll actually not hear it till a bit later. This actually happens if you ever listen to planes flying overhead. Notice when you look up to where you hear it, the plane is often well ahead of where you look. And so the sound, of course, drags behind here because it has to take time to spread out. But when this line of constructive interference hits you, you hear a loud boom. It's called a sonic boom. And that's one of the ways you know if an object actually travels greater than the speed of sound. Now, this is not some sort of, they call it the sound barrier. There's not some weird barrier that a plane has to push through, or that a car that can go this fast has to push through. But it makes this boom because all of the waves it's creating, the sound waves, constructively interfere along this edge. So you essentially get a boost in amplitude. In some ways, this is reminiscent of the effect that resonance has, although this is a different property here. So let me show you a couple of videos of this in action. It's pretty cool. Here is a wood duck swimming really fast. Why is this a good video? Because you can actually see the waves stretching out behind it. There they go. Look at that. Hustling. Doesn't look like his little feet are pumping underneath the water. So you can see the wave front stretching out behind it. In fact, this duck, pause for me. There we go. This duck is actually swimming faster than the speed of the waves in the surface of this pond. Not faster than the speed of sound, but it is faster than these surface waves, and you get that V following behind it. In a sense, it's like a sonic boom to the water. You actually get a bigger wave right along that edge. Notice all the waves behind it are much smaller. Pretty cool, duck. Thank you. Alright, see you later, duck. Now, here's another one. You'll notice this plane, as it approaches the speed of sound, you get that large compression, all the amplitudes constructively interfering. You get a compression, and in fact, that compression here in humid air forces a bit of a cloud to form. Pretty cool. There it is. Pretty awesome. Maybe one more time. Check that out. Then, we got another one of these. Yeah, this is pretty cool. I know the sound may not be great. This may be worth actually doing your own YouTube on this one. You can look up SSC break sound barrier. You should find one. You know, some of these are protected. I think BBC did this video, and they don't really want people watching it without paying, but here we found one.
The average for the two runs was 763 miles an hour.
This is a car.
They were both faster than the speed of sound.
Here it comes.
Andy Green had shattered the sound barrier.
Pretty cool. When you hear that boom, you know you've broken the speed of sound. It's one of the ways they figure it out during these land speed tests. Another thing that can break the speed of sound, there used to be a plane called the Concorde. It would fly transatlantic.